Hello everyone, this time I'm back with a question from section 15.5, question 9, which asks to find the area of the surface given by this equation, z equals to xy, that lies within the cylinder x squared plus y squared equals to 1. A quick review of how we find the surface area. If the surface is given by function f, function of two variables, then the surface area is given by surface area of the surface over a region D is given by fx squared plus fy squared plus 1 dA. Okay, so that's the whole thing you need to know from this section, and then integration, double integral, the techniques you know to evaluate double integrals. For this specific example question, my function is xy, so my function fxy is given by this. Then that means my partial derivative of my function with respect to x is y, and with respect to y is x. And then the integrand that we are going to use is y squared plus x squared plus 1. So that's my integrand. Now let's do the region. What does it mean lies within the cylinder? So that part of surface I have to take out and then determine what is region with respect to that. Let's see what is that cylinder. It is called cylinder because it doesn't have z component. So basically you find what is the graph of this guy on xy plane and then just repeat it on all z's. It doesn't matter what is the form, but you will repeat everything on all heights. So in this case, x squared plus y squared is equal it gives a circle, yes? Now, if you consider that circle and repeat it on every value of z, you will get real cylinder, yes? Okay, but what is important for us? Okay, this region, that surface, I don't know what is the form of that, but it is going to be something about this thing. And the region that I'm going to integrate over is nothing but this disk. So my region here then is all x and y's such that x squared plus y squared are less than equal to 1. It is inside the circle. Okay, so if I want to integrate with respect to that, evaluate my integral with respect to that, since this region is circular, we know that for circular region we are better to use the polar coordinate. So if I want to write this in polar coordinate, r theta, I need to know that r goes from 0 to 1, this is r, and then theta, since we go around the circle once, it will go from 0 to 2 pi. Okay, now everything is set up. I can start evaluating the area, surface area. So I have double integral root of x squared plus y squared plus 1 dA. Then, as I explained before, we decided to go with polar coordinate. In polar coordinate, we have to change three things. First, write the boundaries for iterated integral. They are given here. So theta goes from 0 to 2 pi, r goes from 0 to 1. Second would be change all the variable in your integrand to new variables, r and theta. So meaning that for x write r cosine theta, for y write I sine theta, and use that thing. So r cosine theta squared plus r sine theta squared plus 1. That's second step. Third step would be write the surface element in polar coordinate. And you have to know that surface element in polar coordinate is r dr d theta. Everything is written in polar coordinate. I can simplify, and so I go from 0 to 2 pi, 0 to 1. This part here, r squared cosine squared plus r squared sine squared. You factor out r squared sine squared plus cosine squared is 1, so our old friend is here. That's my integrand, and then r dr d theta. That's the double integral we have to evaluate. Now, I can start evaluating that. Do the inner one. Okay, how can I find the inner, how can I evaluate the inner integral? It is square root of r squared plus 1 multiplied by r. So everything you can see, this derivative of this guy, r squared plus 1, is 2 times of this guy. So that is a good sign to go with substitution as this. Then du would be 2r dr. So I have 0 to 2 pi. Then r dr here, it is half of du. And square root of r squared plus 1 is nothing but square root of u. Let me write this here closer. And then I have d theta. Okay, but there's one more step. Since I use substitution, I have to change boundaries. So here in this case, if r is 0, then u is going to be 1. Plug in r here, 0, you get 1. If r is 1, then u would be 2. So my boundaries are going to be from 1 to 2. This is lower boundary goes to lower boundary, upper boundary goes to upper. Okay, so everything looks good now. I can integrate root u. It is u to the power half, so antiderivative of that would be 1 over half plus 1, u to the power half plus 1. I have another half here, so I put that half there, and then go from 1 to 2. Okay, let's simplify this. 0 to 2 pi. This is 3 over 2, cancel 2 is 1 over 3. U to the power 3 over 2. So I can plug in those numbers there. So it is 2 to the power 3 over 2 minus 1/3 1 to the power 2 over 3 over 2. Okay? And then d theta. Okay, we can simplify these things. For example, this guy is 1/3, so this is 1/3. So I can write 1/3 of 2 to the power, this is 2 root 2 minus 1. That's the number. And then there is no theta dependence, so I can write this out of integral and then do that. And antiderivative of 1 is theta. If I use fundamental theorem of calculus, it would be 2 pi minus 0. Okay, so very quick wrap up. This is the formula we get surface area. So to do that, I have to first see what is f. find the integrand. Integrand is given by this formula for this example. Then the next step is what is the region? Region is described by these words. The part which lies within the cylinder x squared plus y squared equals to 1. So that cylinder is this, and the region I'm going to integrate over is this disk. Since it's circular, I better to write it in polar coordinate. I rewrote my double integral as iterated integral in polar coordinate and evaluated that. And that's the surface area of that surface within the cylinder. Have a great time. Thank you.